Hello students, welcome back to JCE Connect series of lectures. So we'll continue design problems. So let us take one more design problem as a room measuring 7 meter by 10 meter consists of 12 centimeter thick RCC slab supported on a steel beams as shown in the figure at a spacing of 2.5 meters center to center. The floor finishing load may be considered as 1 kN per meter square and live load as 2 kN per meter square. Design intermediate steel beams and assume the yield stress of the steel as 250 Newton per millimeter square and a bearing as 230 millimeter. So this is the design problem given here. The room dimensions are given and intermediate beams are supporting the slab. Okay, so here we need to design the intermediate beams. So this is the figure given in this problem. So this is the room size. So 10 meter by 7 meter room size and the bearings on either side. So this side also, this is a support bearing, a bearing, so assuming as a 230 millimeter. So in both the direction, let us take this as a x direction, this is a x direction, this as a y direction. Okay, so both the directions the bearings are being taken 230 millimeter, and these are the steel beams marked, and the spacing of these beams given as 2.5 meter center to center. So this is the total room size 10 meter by 7 meter. So here the loads are also been given. Let us take the solution. So here the effective span will be clear span plus bearing. The clear span here is a 10 meter is a clear span plus bearing. This side is 0.23 and this side is a 0.23. The effective span will be the center to center distance of support. Suppose this is the beam, this is the beam and this is the support. From center to center, whatever the length you take, that will be the effective length. This one. Okay. Next, assuming 230 millimeter bearing, so the effective length will become 7 plus 0.23 in y direction. That is 723 means along the shorter length, 7.23 meter means along this direction, from here to here, 7.23 meter. Then the next, once you calculate the effective length, so next step will be the load calculations. Floor finish is given, that is a 1 kN per meter square the floor finish to be taken. If not given, you have to assume the floor finish is between 0.8 to 1 kN per meter square. Since in this problem the floor finish is given, let us take that the same value, and the live load is also given 2 kN per meter square. Then the weight of RCC slab, you need to calculate the weight of RCC slab because that intermediate beams are supporting the RCC slab. These intermediate beams are supporting the RCC slab. It is been given in a problem, that is a 7 meter by 10 meter room measuring, and which is consists of 12 centimeter thick RCC slab. So this is intermediate support, the intermediate beams are supporting the RCC slab. Hence you need to calculate the weight of RCC slab. To calculate the weight of RCC slab, so the thickness multiplied by the density. So density multiplied by the thickness gives you the weight of the RCC slab per meter square. So here the thickness given as a 120, that is a 12 centimeter multiplied by the density of the RCC, that is RCC density will be 25 kilonewton per meter cube. So when you multiply the 25 with the 25 by 0.12, you will get 3 kilonewton per meter square, because the density of RCC will be 25 kilonewton per meter cube. Then the total load becomes, means add all the loads, that is the floor finish, live load, and the weight of RCC slab. The weight of RCC slab is nothing but the self weight, then the live load, then the floor finish. All together you will get 6 kilonewton per meter square is the total load acting over the intermediate or over the beams. Then each intermediate beam will take 2.5 meter, that is center to center of spacing. The 2.5 meter is center to center of spacing given. So each intermediate beam will take 2.5 meter center to center spacing, that is 2.5 meter center to center, 2.5 meter width of slab load. Therefore load on each intermediate beam, you have to calculate load on each intermediate beam, that is the total load multiplied by spacing of beams. So when you do the total load multiplied by the spacing, you will get 15 kilonewton per meter. So the 2.5 meter width of the slab will take the load. Therefore the total load, that is load on each intermediate beam, that is total load multiplied by spacing of beams, will give you the 15 kilonewton per meter. Assuming the self weight of the beam, so you have to assume the self weight of the beam also, that is 0.8 kilonewton per meter. Then the design working load will be 15 plus 0.8, you will get 15.8 kilonewton per meter. Then make it factor. So on safer side you have to make it factor. So this is a total factored, or the design factored load will be 23.7 kilonewton per meter. Next will be, so calculate the maximum bending moment. Since that support, that is intermediate beams will be simply supported, they are simply supported beams carrying a UDL of 23.7 kilonewton per meter. So 23.7 kilonewton per meter. This is simply supported carrying a 23.7 kilonewton per meter. Then the maximum bending moment, calculate maximum bending moment for this one. This is the maximum bending moment. So for this one, so generally we get maximum bending moment, this WL square by 8. Calculate the WL square by 8. This is the maximum bending moment we have to get. Then the required plastic modulus of the section we need to calculate. So based on this modulus of section, we choose the section. So this represent the strength. Okay, so this modulus of section will represent the strength of the member required. So that will be calculating by m into gamma m divided by FO. Then we get this much is the section modulus, and the beam section to be chosen which is giving more than this one. So you have to refer IS 800 2007 page number 138. You have to choose the section of the based on the plastic section modulus. So let us try ISMB 350 at 52.4 kg per meter, and the properties of this section will be depth will be 350 millimeter. Means note it down. No, take all the properties from the code or the refer steel table and note all the properties: width of the flange, thickness of the flange, thickness of web, then the elastic section modulus and the plastic section modulus. Then also take the moment of inertia about the major axis, then take the root radius of the section. You know how to take these all properties because we have solved many problems, and you know how to take these properties and all from the steel table or else from the IS code 8, that is I 800 2007. Then after taking the property, then the section classification, to do the section classification, the chosen section lies whether in a plastic compact or a semi compact. We have to decide based on the uh, different element ratios, that is flange element ratio and the web element ratio. For that you calculate the epsilon value. The value will be 1 root of 250 by fy. We know the yield stress of the material, so 250 by 250 will give you the 1. Then the outstand of flange, take the outstand flange, that is the half of the width, this much is the outstand of flange. Then the depth of web to be calculated, and h minus 2 times of tf plus r1. Then take the depth of the web, then you calculate the ratios. These ratios helps us to decide the classification of the section. Since these two ratios are giving the value of that is a flange ratio, flange to thickness ratio will be 4.92, which is less than the 9.4, and the depth to thickness of web will give the 36.24, which is less than 84, which represents the chosen section is a plastic section. Hence for a plastic section the value of beta will be 1. Since one more check we need to do, that is depth to thickness ratio of web, and this based on this ratio we have to decide whether the check for web is required or not. And as per the code, the limit for web check for a buckling is given as a less than 67. If this ratio comes out to be less than 67 epsilon, so we need not be checked for buckling. So if the ratio is coming more than 67 epsilon, so we have to check for the web buckling. In this case it is giving less than the 67 epsilon, hence check for web buckling is not required. Okay, so after this, next we go for the check for shear capacity. Next we go for the check for shear capacity. So for shear capacity, for a simply supported beam, as we know the beam is simply supported carrying UDL of W, the support reaction will be WL by 2, WL by 2. Then the maximum shear force acting will be V equal to WL by 2. We know the value of W, that is the total load coming on the beam, that is 23.7. Then we get the shear force as 85.67 kilonewton. Then the design shear strength of the section, whatever the section we have chosen, what is the strength of that section in shear, that is Vd is Fy by root 3 gamma mo into H into Tw. Then H is the whole section depth, then thickness of web, substitute here, then get it. So we here we get 372 kilonewton, so which means the design shear strength of the chosen section is greater than the whatever the shear force is actually acting. Hence the chosen section is safe in shear. After this, the next will be check for high or the low shear. So whether the chosen section is giving a high shear or the low shear, we have to check that one. For checking that whether the given section is high or the low, we have to take the 60% of the design shear, whatever the design shear we have calculated previously, we have to take the 60% of that. The 60% of design shear gives you the 223.2 kilonewton, which is the less than the actual shear acting. So therefore the case is of low shear. So this is one check we need to, and based on this high or the low shear, we apply the formula to get the design bending strength. So since it is a case of low shear, so the design bending strength can be calculated by using this formula. So we know that we are very familiar with this formula. We have used many times this formula to calculate the design bending strength. This formula to be used when the section is giving low shear. So where beta is the, for a plastic section the value of beta will be 1, where the ZP we know the ZP where for the chosen section, then the Fy is the yield stress. Substitute all the values, we get the design bending strength, and this design bending strength which is to be compared with the this value, and this value, this is for the simply supported, and this whatever the design bending strength we calculate is which should be less than or equal to this much. Then calculate one this value also, and we are getting this value as 212.45. Okay, then this is 212, and here we are getting MD as 202 kilonewton meter, but the limit whatever this one is given, this is giving 212.45 kilonewton meter, hence MD to be taken the least of these two, that is 202.18 kilonewton meter will be the design strength of the chosen section. And this is the design strength of the chosen section, that is bending, but actual bending will be how much? 154.85 kilonewton meter, hence the chosen section is safe in bending. Then next is very important, check for the deflection. So allowable deflection for the simply supported beam will be the L by 300. This is the allowable deflection as per the code. This much is allowable, but actual deflection how much to be is acting for a simply supported beam. The deflection at the middle will be 5 by 384 into WL raised to 4 by EI. This is the formula we use to calculate the maximum deflection for a simply supported beam carrying UDL. Then substitute all the values here, we get 20.62 actual deflection, which is less than the permissible deflection, hence the chosen section is safe against the deflection. Okay, so this is how we have to design the beam. And generally this type of problem will be asked for 15 to 20 marks. The room size will be given, and all floor finish, live load, dead load, everything will be given. Just you have to take the total load, then you have to make it factor. Then after making a factor, you have to calculate the bending moment, and then the bending moment helps us to calculate the section modulus, plastic section modulus, and based on that section modulus we choose the section, and that section modulus indicates the strength of the member, and based on that we choose the section. Then we have to go on checking that chosen section. So if it comes to be safe in all the checks, hence the chosen section is safe and can be used effectively. So finally we have to make a comment like this. I hope you understood this problem. So again we'll continue some more design problems of this type in the next class. Thank you.